Hello students! In the last video, you were introduced to rational numbers and irrational numbers, but we never really developed any strategies on how we could determine whether a number was rational or irrational. In this video, we're going to develop two strategies in order to do so. Let's get started. Strategy number 1. Looking at the decimal. If you recall, 0.123 and 0.333 repeating were rational, but the numbers pi and the square root of 2 were not. Why is that? Well, the rationals have the characteristic that their decimal digits either terminate or are repeating. The irrationals have decimals that do not terminate or repeat and go on forever. But wait, doesn't 0.333 repeating go on forever? Well, yes, it does. But the digits repeat, which is all we need in order to conclude that 0.333 repeating is rational. Strategy number 2, evaluating the radical. Before we take a look at this strategy, I'd like to take a moment to review some of the notation for looking at radicals. Remember that radicals are just numbers with a root symbol outside it. The number inside the radical symbol is the radicand, and the little number on the top left is what type of root we are looking for, and we often refer to this as the index. An example of a radical using this notation is the third root, or the cube root, of the number 8, which is 2, because 2 times itself 3 times is equal to 8. In general, if there is a number, let's say n, as the small little number, the index, we are looking for the nth root of the radicand. That is, we are looking for a number multiplied by itself n times in order to get the radicand. Now, let's take a look at some strategies for evaluating radicals, and for that, we're going to turn to my whiteboard. Okay, so we're taking a look at our first two examples here, and on the whiteboard, I see that I have, as example number 1, the square root of 625, and in example 2, I have the square root of 9 over 100. Let's take a look at the first example. Well, if I entered this into a calculator, or if I remembered my perfect squares up to a ridiculous number, well, I would see that the square root of 625 is 25. And 25 is an integer, and we can write any integer as itself, 25, over the number 1. And what we see is the top number and the bottom number are both integers. And when we have that both numbers are integers, well, that's precisely the definition for a rational number. So because both the top, the numerator, and the denominator are integers, that means 25, so therefore, this is my symbol for therefore 25 is rational. And because 25 is rational, so is 625. 625 is rational as well. Okay. Example 2, I see that I have a square root, and there's a fraction inside the square root. So when this happens, I can break down this fraction inside the square root as 2 individual square roots. So then I have the square root of 9 over the square root of 100. Well, I actually know my perfect squares up until these numbers. They're not too bad. I see that the top is going to get me the square root of 9, which is 3. And on the bottom, I'm going to have the square root of 100, which is 10. And well, for the same reason as example number 1, I have an integer here, and I have an integer here. That means I have 2 integers, which means that the square root of 9 over 100 is rational. And this is for the same reason as example number 1. Okay, moving on to example 3, I see that I have the cube root, because the 3 is outside of the radical, I have the cube root of 26. Well, I remember my cube roots. I know that the cube roots kind of go with 1 as this cube root of 1. I also know that 2 is the cube root of 8 because 2 times 2 times 2 is 8. And I see that 3 is the cube root of 27 because 3 times 3 times 3 is 27. And so this 26, well, that's just a little bit smaller than the 27, but it's definitely bigger than 8. So this cube root of 26 has to go between these two numbers, but I don't know the exact decimal number for that, or the fraction if it is rational. So I'm going to enter this into my calculator. To do that, I have the cube root function. So if I hit cube root, and then I hit the number 26, it will get me this ugly number, or at least I think it's ugly. This is going to get me that the cube root of 26 is, it is 2.96249. And that doesn't look like it has any distinguishing pattern, and it looks like it kind of goes on forever. From my first strategy, in strategy 1, I can make the conclusion that this number, because it doesn't terminate and because the digits aren't repeating, that it's irrational. So let me write that down as a note. So with this number I have right here, which is this number right here, it is non-terminating, as in it doesn't stop, and is not repeating. From this, I can make the conclusion that therefore the cube root of 26 is, and I'm going to write this in red, irrational. As in, it is not rational, as in I cannot write it as a fraction between two integers. Okay? So that's example 3, and now let's take a look at example 4. Now I'm looking at example 4, which is the square root of 9 over 1,000. So that looks really similar to example number 2. So I can initially start looking at this problem by writing this as the square root of 9 over the square root of 1,000. And the square root of 9 we've seen before, that's from example 2. That means that this number, I'm going to write it over here, that will have 3 over the square root of 1,000. Well, if I were to enter the square root of 1,000 into my calculator by hitting the square root button and then 1,000, I would see that the square root of 1,000 is some decimal number. It's 31.6, and I don't really care about the rest of it. Well, that is a decimal, so maybe I can sort of estimate this. This is 3 over 31.6, and what I notice is this number, the 3, is an integer, but this is not an integer because it has a decimal. And if we remember our definition for a rational number, well, a rational number requires that both the numerator and the denominator, they both must be integers. So I can conclude that this is not a rational number. So therefore, the square root of 9 over 1,000 is irrational. Okay, so I've just figured out that this number is not rational. Alright, so I finished with all my examples, and I'd like to point out that in example 2 and in example 4, I split up the radical into 2 separate radicals. We'll be seeing a lot more of that in the next lesson when we talk about mixed and entire radicals. For now, I hope that you have a great day, and I'll see you in the next video. Bye!